हेलो स्टूडेंट्स। आज हम लोग डिस्कस करेंगे डिफ्लेक्शन ऑफ बीम्स। आज का टॉपिक है हमारा डिफ्लेक्शन ऑफ बीम्स। ओके, तो डिफ्लेक्शन ऑफ बीम्स के लिए फर्स्ट ऑफ ऑल व्हाट इज डिफ्लेक्शन ऑफ बीम? Let us consider a simply supported beam having a point load of magnitude W. So due to this point load, this simply supported beam will be deflected like this. Okay, consider a initial point C. Now this point will be vertically displaced due to this point load, due to this deflection. This displacement of this point is known as deflection. Okay, deflection of beam. तो जब भी किसी बीम पर हम लोड अप्लाई करते हैं तो लोड अप्लाई करने से बीम में डिफ्लेक्शन प्रोड्यूस होते हैं और साथ ही साथ किसी भी पर्टिकुलर पॉइंट पर अगर हम देखें तो एक स्लोप भी जनरेट होता है. स्लोप इज द एंगल ऑफ द टेंजेंट फ्रॉम द पॉजिटिव एक्स एक्सिस. ओके, सो अब इस चैप्टर में हम लोग डिस्कस करेंगे बीम्स में डिफरेंट डिफरेंट पॉइंट्स पर लोड और लोड अप्लाई करने से डिफरेंट डिफरेंट पॉइंट्स पर डिफ्लेक्शन और स्लोप का मैग्नीट्यूड कैसे फाइंड आउट करते हैं. तो सबसे पहले रिलेशन बिटवीन स्लोप, डिफ्लेक्शन and radius of curvature r. Okay, the relation between slope, deflection and radius of curvature is let the radius of curvature of a beam is r. Okay, radius of curvature of beam is r and the deflection of the beam is at a point at a distance x from the point A, the deflection is y and the radius of curvature of the beam is r. Then in this case 1 by r is equal to the d2y upon dx square. Okay. From bending equation we know that m upon I is equal to E by R. Now from this equation, bending moment about the section x will be E into I d2y upon dx square, where y is the deflection at a section which is at a distance x from the point A. Okay. Now take first case for a cantilever beam. Cantilever beam. There are three methods to determine deflection and slope at a section of a beam due to the loads condition. First method is double integration method. Second method is Macaulay's method. And the third method is area moment area method. First of all, we are using double integration method for determining the slope and deflection of a cantilever beam having a point load at its free end. Okay. Slope and deflection. Okay. Let us consider a cantilever beam of length L having a point load at its free end of W. Okay. Due to this point load, beam will deflect like this. Let deflection at the point any point, any section. Suppose section is at a distance x from the point A. Okay, let us consider a cantilever beam of length L having a point load at its free end. Consider a section at a distance x from the point A, and the deflection at this point is y. Okay. Now bending moment about this section will be is equal to E into I into d2y upon dx square from above equation, equation number 1. where E is the modulus of elasticity of the beam and I is the modulus moment of inertia of the cross section of the beam about its neutral axis. Okay, we know that moment about the section XX, mx will be is equal to the minus w into x, force into perpendicular distance, equation number 2. These two equation moment about this section xx will be minus w into x. From the equation number 1 and 2, these two values are equal to each other. So ei into d2y upon dx square will be equal to the minus w into x. Now for determining the slope and deflection, integrate this equation with respect to x. Now ei dy over dx is equal to the minus wx square by 2 plus c1. Equation number 3. Now applying the end conditions for determining the value of the c1. C1 is the integration constant. Okay, so in a cantilever beam at x is equal to L, deflection of the beam is 0 because point B is a fixed end, and the slope, it means dy by dx is equal to 0, also is equal to 0 because B is a fixed point. And at a fixed point, the slope as well as the deflection of the beam is 0. So using this and condition, at x is equal to L, dy by dx is equal to 0. Now from the equation number 3, ei into 0 is equal to minus w L square by 2 plus c1. Now from this equation, c1 is equal to the wl square by 2. Okay, so from the equation 3, ei into dy by dx is equal to the minus wx square by 2 plus wl square by 2. Now integrate this equation about x. Ei into x y will be is equal to the minus wx cube upon 6 plus wl square by 2 into x plus c2. C2 is the integration constant. Now using the end conditions, at x is equal to L, deflection of the beam is 0. Now ei into 0 is equal to the minus wl cube by 6 plus wl cube by 2 plus c2. Okay, c2 is equal to the wl cube 1 by 6 minus 3 by 6. So C2 is equal to the WL cube into minus 2 by 6 or minus 1 by 3. So C2 is equal to the minus WL cube upon 3. Now putting this equation value in equation, deflection equation, EI into Y is equal to the minus WX cube upon 6 plus WL square X by 2 WL square minus WL cube by 3. This is the deflection equation, and the slope equation is EI into dy by dx is equal to the minus WX square by 3 2 plus WL square by WL by 2, not WL square by 2, WL. Wait a minute, what is the value of C1? WL square by 2 is equal to the WL square by 2. Okay, WL square by 2. This is the equation for slope, and this is the equation for deflection for a cantilever beam having a point load at its free end. Okay, now in a cantilever beam having a point load at its free end, deflection will be maximum at its free end. It means at the point A where x is equal to 0. Now putting this value in equations of slope and deflection, and slope is also is greater maximum at the point A. If we draw a tangent at this point, slope is also is maximum at the free end. Now putting the at x is equal to 0, EI into y is maximum at this point. So first 0, second point function is also 0, minus WL cube by 3, WL cube by 3. Then y maximum deflection will be equal to minus WL cube upon 3 EI. So in the case of a cantilever beam having a point load at its free end, the maximum deflection will be equal to the minus WL cube upon 3I. Minus sign is showing here that the deflection is in downward direction. Okay, maximum or minus sign is shows here that the deflection is in minus direction, in downward direction. Okay, now from the slope equation, the slope will be EI dy by dx. This will be the maximum slope at its free end, 0 WL square upon 2 plus WL square upon 2. So the slope will be at the free end is equal to the WL square upon 2EI. Here, what will be the slope? What is slope? Slope is the angle between tangent at that point from the positive x-axis in anti-clockwise direction. So here this angle is positive angle. Okay. So the maximum slope in the case of a cantilever beam having a point load at its free end is WL square upon 2EI. Okay. Now the second case is a cantilever beam having a uniformly distributed load at its whole length. At its whole length, we have to determine the slope and deflection at its free end. So in this case, let us consider a cantilever beam of length L having a uniformly distributed load of intensity W Newton per meter. Okay. The deflection in this case will be maximum at its free end. Deflection and slope both are maximum at this end, free end, and at the fixed end where x is equal to L, deflection and slope both are equal to 0 because the fixed end is other end is fixed. Okay. Let at a distance x from the point A, about a section XX, deflection of beam is y. Okay. Now from deflection equation, we know that bending moment about the section XX will be equal to the mx is equal to the EI d2y upon dx square, equation number 1, and bending moment about the section axis due to the load, uniformly distributed load, mx will be equal to the minus wx square by 2. Okay, this is the equation number 2, equating the both the equations. So EI d2y upon dx square will be equal to the minus wx square by 2. Okay, now integrate this equation 3 about x with respect to x. EI dy by dx is equal to the minus wx cube upon 6 plus c1. Applying the end condition at x is equal to L, slope is 0. c1 is the integration constant here. So c1 will be minus WL cube by 6 plus c1 implies c1 is equal to the WL cube by 6. Okay, WL cube by 6. Now EI dy by dx will be equal to minus wx cube upon 6 plus wl cube by 6, equation number 4. Now again integrate the equation number 4 with respect to x for determining the deflection equation. So EI into y is equal to minus wx की power 4 upon 24 plus wl cube upon 6 into x plus C2. C2 is the integration constant. Now for determining the integration constant, applying the end condition at x is equal to L, y is equal to 0. So WL to the power 4 upon 24 plus WL to the power 4 upon 6 plus C2. C2 is equal to the WL to the power 4 1 upon 24 minus 4 upon 24 multiplying by 4 divided by 4. Now C2 will be is equal to the WL to the power 4 into minus 3 upon 24. C2 will be minus WL by 4 L की power 4 upon 8. Now the deflection equation will be EI into y is equal to the minus WL to the power 24 plus WL cube upon 6 into x minus WL to the power 4 by 8. Okay. And the deflection equation will be, slope equation will be EI dy by dx is equal to minus WL cube upon 6 plus WL cube by 2. देख लेते हैं क्या इक्वेशन वैल्यू है. WL cube by WX cube by 6 WL cube by 6 WL cube by 6 है यहाँ पर WL cube by 6. This will be the equation for determining the slope at any point in the case of a cantilever beam having a uniformly distributed load over its whole length, and this will be the deflection equation for determining the deflection at any point in the case of a cantilever beam having a uniformly distributed load over its whole length. In the case of a cantilever beam, the deflection and the slope is maximum at its free end. Now applying the end condition, determining the slope and deflection at its free end. At its free end at the point A, x is equal to 0. Then from the deflection equation, the deflection will be is equal to the minus WL to the power 4 upon 8 EI. Okay, 8 EI. Okay, this minus sign shows shows that the deflection is in downward direction. Okay, now the slope at its free end will be is equal to the dy by dx at the point A. Dy by dx is equal to the WL square by 6EI. Okay, this will be the maximum slope at its free end, and this is the maximum deflection at its free end. Okay, now we have considered a special case for a cantilever beam where a point load is acting at a distance a from its free end. Let us consider a point load W acting at a distance a from the free end. Okay, let us consider a cantilever beam of length L having a point load at a point at a distance small a from the point A, from the point free end, yeah, from the free end. In that case, deflection at the point C will be okay. Deflection at the point C will be okay. CC dash will be is equal to the we have considering we have uh, we are calculate already calculating this value in the case of a cantilever beam having a point load at its free end. Okay, now the deflection is WLQ upon 3EI. Okay, WLQ upon 3EI, and the slope is WL square upon 2EI. Now, so CC dash will be minus WLQ upon 3EI, and the slope at this end is this point will be equal to the minus WL square upon 2EI. Now, the deflection at the point A can be calculated from the for the section AC, because there is no load beyond this point C between AC. The section AC will go straight like this, in straight like this. Okay, draw a perpendicular from the CC dash, the point D. AD will be equal to CC dash, and in this case the deflection at the point is equal to the distance AE, and the distance AE is equal to the AD plus DE. AD is equal to CC dash, and D can be determined by this right angle triangles DEC dash. Okay, okay, YA. Here, this length is A. Okay, this length is A. We have to determine this value DE. The angle at this point C, theta C, is known, which is equal to WL square upon 2 EI. Okay. So, if theta C is WL square upon 2 EI, then from this right angle triangle, sin theta C will be equal to the D upon EC dash, or DE is equal to the EC dash into theta C. Here theta C is very small and sin theta will be theta. Okay. So DE is equal to the A into WL square upon 2 EI. Now YA is equal to the WL cube upon 3 EI plus WL square into A upon 2 EI. This will be the deflection at the free end A. Okay. And the slope at the point A will be equal to the slope at the point C. It means the slope at the point A will be is equal to the WL square upon 2 EI. Okay. Now, consider a simply supported beam having a point load at its mid of span of W. Let us consider a simply supported beam of length L having a point load W at its mid of span. In the case of a simply supported beam, deflection is maximum where the point load is acting. In the case of a simply supported beam, when the load is in symmetrical condition, in that case, deflection will be maximum at the middle of the beam. Okay, and the slope is maximum at the ends points. If the load is acting in symmetrical condition, the slope at the point A and B, both the ends are equal to each other. Okay, and the slope is 0 at where the deflection is maximum in the case of a simply supported beam. Okay, now here if we consider a section XX at a distance x from the point A, okay, and the deflection at this section is y, okay, in that case moment about this section XX will be equal to the EI into d2y over dx square. Equation number 1. And we already know that in the case of a simply supported beam, when a point load is acting at its middle, then in that case reactions at the points end points are W by 2 and W by 2. We already discussed this in shear force and in the topic of shear force and bending moment diagram. Okay. Now the bending moment about the section XX will be equal to the W by 2 into X. This will be the equation number 2. Now equating the equation 1 and 2, EI d2y upon dx square is equal to the Wx by 2. Equation number 3. Now integrate this equation with respect to x. EI dy by dx is equal to the Wx square by 4 plus C1. Here C1 is the integration constant. Okay. For determining the value of this integration constant, we have to apply the end conditions. Now, in a simply supported beam, the end conditions are at the points at the point A where x is equal to 0, at the point A where x is equal to 0, the slope at the point A is deflection at the point A is 0, but the slope at the point A will be the maximum. Okay. At the middle of the simply supported beam, in where here the point load is acting in the middle of the beam, uh, so in that case the at x is equal to L by 2, deflection will be maximum at this point and the slope is 0 at this point. And for the point B where x is equal to L, here deflection is 0, but the slope will be the maximum. Okay. Now here at x is equal to L by 2, dy by dx is equal to 0. Okay. Now applying this condition, W by 4 into L square by 4 plus C1 implies C1 is equal to the minus WL square by 16. Now putting this value in equation number 4, EI dy by dx is equal to the Wx square by 4 minus WL square by 16. We can calculate slope at any point by this equation. This will be the slope equation. Okay. Now again integrate this equation with respect to x for determining the deflection equation for a simply supported beam having a point load at its mid of span. EI into y is equal to the Wx cube upon 12 minus WL square by 16 x plus C2, where C2 is the integration constant. Now for determining this integration constant, we are applying the end condition where x is equal to 0, deflection is 0. At x is equal to 0, deflection is 0. So from here, C2 will be equal to the 0. Okay. Now from this above equation, EI into Y will be equal to the WX cube by 12 minus WL square into 16x. This will be the deflection equation for the simply supported beam having a point load at its mid of span, and the deflection slope equation will be EI dy by dx WX square by 4 minus WL square upon 16. Okay. Now at for determining the maximum deflection is in the case of a simply supported beam, when a symmetrical load is applying on a simply supported beam. In this case, deflection will be the maximum where at the middle of this beam. Okay. So at x is equal to L by 2, deflection will be maximum. Now calculating the deflection is at that point using the equation number 6, EI into y maximum is equal to the W upon 12 into L cube upon 8 minus WL square upon 16 into L by 2. Okay. Now solving this equation, WL cube will be can be common from this equation. 1 by 12 into 8 minus 1 by 16 into 2. Okay. Now WL cube upon 8 into 4. This will be the 1 by 3 or minus 1. Okay. Now multiplying by 3 and divide by 3, WL cube upon 32 into minus 2 by 3. Okay. This will be minus WL cube upon 48 divided by EI. This will be the maximum deflection in the case of a simply supported beam having a point load at its mid of span. Now the slope is maximum at its endpoints. At x is equal to 0, slope at the point A will be can be calculated by using the equation number 5, WL square by 4 minus WL square by 16. So slope at the point A will be minus WL square upon 16 EI. Okay, here minus sign shows that deflection at the point A is greater than 90 degree, and this slope is calculating from the minus x-axis in clockwise direction. This minus sign shows here that this angle is calculating from the minus x-axis in clockwise direction. Okay. Now the slope at the point B x is equal to L will be equal to the WL upon 16 EI, WL square upon 16 EI. Here plus sign shows that the deflection at the point B will be calculating from the positive x-axis in counterclockwise direction. Okay, the magnitude of the slopes at the endpoints will be equal to each other when the load is acting symmetrically. In that case, when the simply supported beam, in the case of a simply supported beam, slope is equal to the at both the endpoints. Okay. Okay. Now we know that in the case of a simply supported beam having a point load at its mid of span, the maximum deflection at its mid of span is minus WLQ upon 48 EI, and maximum slope is theta A is equal to the WL square upon 16 EI at its ends. Okay. Okay. Thank you very much.